Let's now take a look at nitrogen nucleophiles and how they might react with ketones and aldehydes. I'm going to use an aldehyde as my sample carbonyl species in this case, but of course a ketone should have the same reactivity. So we react a nitrogen nucleophile such as ethylamine with a ketone or aldehyde in the presence of acid, and we end up with this species here. That should be an ethyl. We call this an imine, and we give off water just like we did with the acetal formation. And one cool reaction we can do with this imine is NaCnBH3 in mild acid. We can actually reduce the CN double bond to a CN single bond, and now we've made an amine. And that's interesting because we have not yet learned how to make amines, or at least extend amines chains very easily. So this is one way that we can add another R group to an amine. All right, let's look at this mechanism. We're going to start by protonating, of course, just like we did with the aldehyde, the ketone plus alcohol reaction we just looked at on the previous video. Here I have a better electrophile. This is a proton transfer step. And now I can take my nitrogen nucleophile, add to my aldehyde, and now you see I have a protonated intermediate. I need to proton transfer that. I could use the nitrogen, that's probably most likely, as a temporary weak base. This is a proton transfer. And I have a protonated ethylamine here. I'm going to keep this right here because I'm going to use that extra hydrogen now to protonate my OH to make water, to eventually lose water as a leaving group. Again, we're following the same sequence of steps as we followed for the acetal formation. And if you remember now, we're going to lose water by forming the double bond between the heteroatom and the carbonyl carbon. This is loss of leaving group. And this is a very similar step to what we saw in the acetal formation, except here we're basically done. All we need to do is remove this H, and then we have our imine formation. So we're just going to, let's use water. We formed water on the previous step. Let's use it here to regenerate our acid catalyst and form our neutral imine. So here's the imine. This again is reversible. This is a proton transfer step. We formed the imine and we formed water in the process. So again, let's look at the mechanistic steps. We have proton transfer, nucleophilic attack, same sequence that we started with for the acetal, then a proton transfer, then another proton transfer, finally loss of leaving group to get rid of the water. We did that in the acetal. The only difference here is now we're not adding another nucleophile, we're simply removing that final proton to get to our neutral imine. So this is the imine formation, and it does have a pH dependence. 4.5 is ideal. So if we get too high of a pH, meaning there's not a lot of hydrogens around, we're not going to be able to protonate our aldehyde or ketone, and so we won't generate a good electrophile. If the pH is too low, we're actually going to protonate a lot of these amine molecules, and they are not good nucleophiles at that point. So if the pH is too low, meaning there's too many protons around, we can actually protonate some of these amines, and they don't act as good nucleophiles then. Okay, one more thing I want to point out about imine formation is that in practice, sometimes we don't need acid catalyst. And so in graduate school, I did this reaction. Here's the aldehyde. And I reacted that with this aminobenzene, or aniline it's called. And I used no acid catalyst. All I used is ethanol solvent. And I ended up with what you'd expect, the imine. No acid was present in this reaction. So oftentimes imines are great nucleophiles, and if we have an aldehyde or a reactive carbonyl species, we don't even need the extra acid help. All right, let's look at a reaction with a secondary amine. So I'm going to use a ketone now to show you that they both work together, the same. I'm going to use, again, acid catalyst. Let's just show H2SO4 in this case. And my secondary amine will be diethylamine. The product I'm going to make is not the CN double bond, but we actually get an adjacent CC double bond. We call this an ene amine. Ene from the alkene, amine from the fact that we have an amine. And we can reduce this as well using sodium cyanoborohydride, just like I showed you a few slides ago. We actually don't need the stepwise, so I'm going to scribble those out. Some proton source, we can produce simply the amine with no extra double bonds. So this is a tertiary amine. We formed it from a secondary amine, and this is called reductive amination. When you combine the first step of imine formation or enamine formation, followed by sodium cyanoborohydride, it's called reductive amination. And you can see that the ketone ended up right here, and we're simply making a CN single bond where the carbonyl used to be. All right, let's look at this mechanism. It's going to be very, very similar to what we just showed. So the first step, of course, is a proton transfer. I'm going to cheat on that a little bit. We all know how to draw proton transfers at this point. Here's my protonated ketone. I'm going to use the lone pair on the amine. To make my new CN bond. I'm going to proton transfer, probably using, I'm going to use the amine in this case. To get rid of the extra hydrogen here. Now I have a protonated secondary amine, and just like I did with the imine, I can protonate the OH group. Making a better leaving group. And just like I did with the imine formation, I can kick off that better leaving group using the lone pair on the adjacent nitrogen. That's a loss of leaving group. And I can form this cationic species, which is similar to what we formed with the imine, except I don't have a bond to hydrogen on the nitrogen. I have just 4 bonds to carbon, giving me an ammonium cation in this case. And since I know that my molecule needs to be neutral when I am done with the reaction, we need to remove an adjacent hydrogen to push the electrons back onto the nitrogen. So I can do that here, a final proton transfer step. This is a different proton transfer step than the imine formation, but it's still a proton transfer step. So again, the same basic mechanistic steps are present here for the enamine formation, except that the final step is just slightly different. And you can see that we've generated water. We've produced water in this step. And I've regenerated my acid catalyst as I've made my enamine. So here's the enamine that I showed up here. It's got the same mechanistic steps as the imine formation: proton transfer, nucleophilic attack, proton transfer, proton transfer, loss of leaving group, proton transfer. So you see, in these fun with acid problems, again, we're using acid catalysts, so we have a fun with acid problem. We've got many, many opportunities for proton transfer. Those are the majority of the elementary steps in these mechanisms where we add nucleophiles to carbonyl species.